Now in this video, let us define the property of entropy, and for that let us focus on this diagram. In this diagram we have a system that has been taken from an initial equilibrium state I to a final equilibrium state F, okay, by following the reversible path R1. Now the system is brought back from state F to state I by following another reversible path R2. Now these two paths R1 and R2 together constitute a reversible cycle. Okay, and for a reversible cycle from Clausius theorem, we can say for the paths R1, R2, dq by t, it is equal to 0. Now we can split this integral into two integrals, and one integral would be for path R1, okay, and the other integral would be for path R2. Okay. Now for path R1, the integral would be or the end states are f and I. So you will have integral for R1. You start from I and you go till f, and this is dq upon dt, okay, is equal to, now when you bring this on the other side, this becomes a negative sign, and the integral, this is for R2, and it goes from state F to state I, because you have to bring the system back to its initial state. Now because R2 is a reversible path, I can reverse this and write down I to F for R2 dq by dt. Okay, so when you interchange the, or when you flip the limits, the negative sign changes to positive sign. So I can write down this whole equation as integral I to F for R1 dq by dt, or dq by t, is equal to integral I to F R2 dq by t. Now this equation is actually representing, or representing a property. What property is this? Because, but before let's answer that, why is it a property? Now this is a property because it does not depend upon the path we are taking. Whether you take R1, whether you take R2, the value of the property is independent of it. It depends upon the initial state and the final state. So it is a point function, not a path function. Alright, and because it is a point function, therefore this makes it a property of the system, and this property we call the entropy of the system. Okay, so if you have to write it down in mathematical form, so for any reversible path R, any, so from I to F, dq by t is equal to entropy of F minus entropy of I. So this is how you write down the mathematical relation for entropy. And now when the two equilibrium states are infinitesimally near, when you can say the distance between this state and this state is very, very less, then we can write down that integral, or you can say that not integral, let's just write down that dq upon dt, this is equal to ds, because there is very small distance between I and F. So this is when the distance between I and F is infinitely small. Alright. Now a very important thing that we should always remember here is that in the diagram shown above, both the paths were reversible. Okay, so the system was taken from initial state to the final state via a reversible path. But now if the system is taken from an initial equilibrium state to a final equilibrium state by an irreversible path, okay, so let's now say, let's replace the reversible path, okay, and we introduce an irreversible path, and now your system is being carried out or being taken from state I to state F via this irreversible path. Now this is not, or this will not, affect the property of the entropy, because entropy is not a path function but it is a point function. So it is irrelevant of the path followed, and the non-reversible path replaced by a reversible path, okay, we can use it as it is. So this equation would now become integral I to F dq by t, okay, this is equal to the entropy difference for an irreversible path. So you can very well see the difference, that here you had R which emphasized that this is for a reversible process, and here you don't have any R, rather you write irreversible path in the parenthesis of delta S. Okay, so this is how you define the property of entropy. So I hope you understood this concept and introduction to entropy as a definition and as a property of the system. Now in the next video we'll look at some common temperature entropy plots.